And today, there's something in the news showing that grad students had found a counterexample to a famous conjecture. So the advisor had asked them to prove the conjecture, and they found a counterexample. And it was a conjecture people really for many years. I don't remember the name of it, but it's a topology one, all things. All right, so as I went through kind of thinking about how I'm going to construct this, I felt like this set, which is called the Borel sets, that's the minimal sigma algebra that contains open intervals. So it has a name. I think Colonel Clark said this already, Borel sets. It's the minimal sigma algebra containing open intervals. I felt like this would be my counterexample. So I started asking myself, are there things in the Borel sets that I know are in the Borel sets where I can get it to violate property number 2? As so a 1.5 hour car drive, and I couldn't come up with it. So I'm walking around thinking in the hallways, what could be it? It must be property number 3 that blows it. So if you look at property 3, the union, the countable union of sets have to be in there. How is that different than topology, the definition of topology? Could be uncountable. Countable is infinite, right? So could be uncountable. And so I realized my counterexample has to come from property 3. Once I did that, I thought, well, what can I use to generate something? Well, here's where we're gonna have to take a leap of faith. There are subsets of R that are not Borel sets. So all the Borel sets doesn't generate the power sets on R. There's something in there. And the way you prove that is a beast, actually. You compare how many things are in the power set of R itself, and you compare how many things are in the Borel sets by counting. And these are 2 uncountable sets. So you're really comparing an uncountable set to another uncountable set, and you show there's a gap. So it's not an easy proof to show that there is something that's not in the Borel sets, but is a subset of R. But there is one. So that one I actually have to ask you to take a leap of faith.
Do you have an example?
It's actually, we don't have an example. It's not an example. You do use a counting argument to show it exists. So such a set exists.
No.
Like 0 steady.
And you get it. If you like this stuff, I really ended up loving measure theory. I recommend taking it in graduate school. Don't go to a school that doesn't offer it. It's a really good class. I mean, it tells you something about their program. One of the best things, one of the other graduate students told me, she came from Hungary. She had taken all these courses in Europe, and I wanted to take algebraic topology. And she said to me, first you need to know algebra, and then you need to know topology, and then you take algebraic topology, not before. And she said, what the problem is that at Georgia Tech, they gutted out the pre-year program, and they took out algebra and they took out topology as requirements. So most of us didn't have it. And they forgot that they needed it. They forget when they need it, right? So they want to do things with algebraic topology, and we're unable to catch up to them. Go ahead. No, I can't show that for you in this class. That's really out of scope, right? It's really out of scope. But we call it a non-measurable set. So there's a set that's in this Borel set that's not in the Borel set that is a subset of R. So there's something in between the Borel sets. So if you look at the power sets of X, so if you look at P on R, that's the power sets of on R, the Borel set's inside here. So it's not as big as all the power sets. So not every subset is going to be contained. What that subset looks like your guess is as good as mine. I don't think I was ever shown what that set looks like. We show that it exists because what we do is we show that with accountability argument, there's just more things in the power sets of X than there is in the Borel sets. And in fact, there's another sigma algebra that generates something called a Lebesgue measure. That set is also bigger than the Borel sets. So there's something in the Lebesgue measurable sets that is not in the Borel sets. But the Borel sets by itself is really huge. It's humongous. All right, so I have this beast that you're going to believe me for. Call it B. And what I know about B is that that's true. You just did it on the boards, right? But by definition of topology, the union of all those singletons must also be in B. Boom. But it's not. So sigma algebra is not a topology in both directions. You don't have time, I know that's time, all that stuff we talk about. But if you do want a time sink, look up non-Borel set and you'll get a whole bunch of reading on it. It is interesting. Just cancel your weekend plans if you plan to do that. Yeah, I think I have 2 double majors in this class.
Four masses.
And sure, it feels that way.
I have the easiest elevator, so.
Great, should have been yes. It's too late now, sir.
I think it's cool that she's doing econ.
I shouldn't see it. But you want to go 6 months back with me.
Yeah, let's do it.
All
All right, where are we on the fill in the blank?
Or some reduction.
Find the pause now and let you fill in the blank. Okay, yeah, so you can fill in the blank up to number D. Catch up on fill in the blank. Wait, 4 D or 2 T. I think 4 2B, yes. 2B, all the way up to 2B.